Hello, everyone. I hope you can hear me well. My name is Stojan, and today we're going to talk about effortless concurrency with ArrowFX on Android. I'm a software engineer at Axel Springer. I basically build a newspaper app, and I do mostly Android and a little bit of backend work, and as we have server-driven UI. Okay, sorry about that. So, the agenda for today. We're going to introduce a small example. Hopefully it's realistic enough, and all of you may have done something similar in the past or will do in the future. Then we're going to do a simple solution using plain coroutines, as in the Kotlinx Coroutines library. We're going to optimize it with the Kotlinx Coroutines library. Then we're going to introduce Arrow and see if there are some functions there that can help us solve the problem in an optimal way. And in the end, we're going to wrap up with talking about Arrow schedule, which is helpful for resiliency. This is the app we're going to work with. There is a free API called DocCU API, and it offers a few endpoints. In this scenario, we are showing a list of dog breeds, and for each dog breed, we're showing a random image. The UI is built with Compose, but it's not really relevant here. So the API we're going to work with has a few endpoints. One of the endpoints is list all breeds, which basically gives us a list of all dog breeds that are available. As we can see, there's no image here. We only get the names. To get the images, we need to do a second API call. And that API call is random image from a breed. Given a breed name, it will give us an image URL. A Kotlin API for this would look something like this. We can have a breed names function, a suspend function that returns a list of strings, and each element in the list will be the breed names from the API. And we can have another function, suspend function, image URL, that takes a breed name and returns a pair where we have the name and the image URL for the given breed. And to solve our problem, we will need to call the first function, and then for each element in the list, call our second function. And if we want to do the simplest solution we can get away with, it would look something like this. We call our breed name function, and we get a list back. We use the map operator that's executed for each element in the list, and we call the image URL. Because map is inline, this will work, but it has like a slight problem. We have a lot of dog breeds, so it's very, very slow. These are some durations on my machine when I was working on preparing this talk. It takes around 20 seconds, and ain't nobody got time for that. So how can we optimize this? I once tried to explain optimizing this to a friend over a phone. And basically the solution is opening a coroutine scope. We use async to start some child coroutines. And we get deferreds back. And we call await all on those deferreds. And things should just work. And if you're listening to this over the phone, you might implement something like this, where we call the breed names, we use map, we open a coroutine scope, and we call async inside it, and then we call await all on the resulting deferreds. However, this is even slower than the previous one, because it's wrong. The actual solution that we want is something like this. we open exactly one top-level coroutine scope. Inside it, Brit names actually can be also outside. It doesn't really matter. But inside it, we call map and async to start child coroutines. And then we call await all. And this takes roughly 5 seconds to execute everything, which is much better than the original 20 seconds. How does this work, basically? It will execute the image URL function concurrently. That means that depending on the dispatcher, it might get executed in parallel. If you're using something like retrofit, it already has its own thread pool, so it will be executed in parallel. And if one of the child coroutines fails because of an error, basically if it throws an exception, it will cancel the rest of the children, and the whole computation will fail. And this is something that's probably desirable by default, because if you want a list of 20 items and you only get 19, it would be confusing, unless it's what you're intending to do. And we will go on more specific error handling a bit later. Let's talk about Arrow a little bit. It's a set of libraries that are inspired by functional programming communities and that are adapted to Kotlin-friendly way. It has multiple libraries, like Core, ArrowFX, Arrow Resilience, Arrow Optics. I think there are a few more. Arrow Core contains some utilities around typed error handling, and it has some DSLs that make working with the errors in a type-safe way. We will not be covering that today. ArrowFX has some utilities for working with coroutines, mostly around parallel execution and other stuff, also with flows. Arrow Resilience has things like circuit breaker and schedule. Today we will talk a little bit about schedule. Arrow Optics helps us working with deeply nested immutable data types. It basically can provide a copy function that works really nice with deeply nested data classes or sealed classes. So let's take a look at how we can solve our problem using ArrowFX. We have a function, ArrowFX. It returns a list of a pair with a breed name and an image URL. And we call our breed names function from the original example that returns the list. And then we use, instead of map, that will call the image URL function sequentially, we use parmap, which will call them concurrently. Internally, this works in the same way as the optimized coroutines example. And we only did one function change to go from sequential to parallel. We went from map to parmap. I think I could explain this over a phone and nobody would get it wrong. So the main benefit here is less error prone. So what do we do if we want to, let's say, change the error handling and ignore some errors? Let's say a dog has no image, API trolls. If that happens, one way to handle it is to remove that breed name from the list and just show the remaining ones that did succeed. With using just the Kotlinx Coroutines library, we could adjust our function like this. We still open the coroutine scope at top level. We still call our breed names function. Here we're not doing any error handling because if that fails, there is nothing to show. And for the image URL, we do a try catch. And if it fails with an error exception in this example, we return null. We still do the async stuff, so ticks are executed in parallel. And we still do await all. to wait for all the computations and extract the URL from there. And since now we get a list of nullable elements, we can add filter not null to remove all the null elements from the list. Doing the same with arrow would look like this. Instead of par map, we would use par map not null. The naming is inspired by the Kotlinx standard library, where a list has a map operator and a map not null operator, where map not null is like map and filter null. Similarly here, we can use par map not null, and any nullable elements in the list will be filtered. So we call breed names, we use par map not null, we do our usual try catch for the image URL function, and return null in case there is an error exception. And this works in the same way as the previous example. Another thing we might want to do when working with this is if we notice that the breed names has a lot of breed names, and maybe the server starts slowing down if it gets a lot of concurrent requests. Another common thing might be to limit the number of concurrency. So we went from 1 to infinity. Maybe we want to do something like 5, 10, or 25, or whatever number. To do this, the Kotlinx Coroutines library offers the semaphore data type, and limiting concurrency to something like 10 would be as simple as creating a semaphore inside our function. And then when calling our image URL function, we use the semaphore with permit function to limit the concurrency. The way this works is it only allows up to 10 requests at a time, because we have 10 as the concurrency limit. Otherwise, it works exactly the same. If we want to do the same thing with arrow, conveniently, arrow offers a parameter concurrency that has some default value, and we can set whatever number we want there. Internally, this is exactly the same code as the previous slide. It uses a semaphore internally. And other things that we can adjust also is the dispatcher in which the Lambda runs. I don't have an example for that, but it's also possible to set it. So far, we've been talking about working with lists of functions or computations. Now we're going to switch topic a bit and talk about independent computations. So we had a list, and every function in that list was from the same type. We're going to introduce an example now that's not supported by the API, but it's just like to explain a concept. We want to get a random image for a breed once we have a name, and we can also get a fun fact, something fun about that breed. This doesn't exist in the API. We can, of course, do the boring thing and do it sequentially. It's probably not going to take 20 seconds because it's just 2 API calls, but the topic today is let's do it really fast, or as fast as possible. The Kotlin API would look like shown here. We have the same image URL function that takes a breed name and returns its name and an image URL. We also have a fun fact function, which is a suspend function, and returns a string. This is the fun fact. Using plain Kotlinx Coroutines, it's again the similar approach where we open our coroutine scope. Inside it, we can use async to create a deferred. The first deferred will get the image URL. The second deferred would get a fun fact. And then we can create a pair from both of them, and we call await to get the underlying value. And this works well, but it kind of obfuscates the logic a little bit. We have this coroutine scope, we have these asyncs, we have these variables that are introduced that represent the deferreds. Ideally, we would want to focus on image URL, fun fact, and how we combine them together, which is basically the last line. And to do this, Arrow offers a function called parzip. So given a breed name, our function here execute will return a pair of the image URL and the fun fact for the breed. We can use parzip from Arrow, and we pass it two lambdas. The first one is image URL, and the second one is breed fun fact. And we have a third lambda that specifies how we combine the results of the first two lambdas. And here we are using the to operator to create a pair from the image URL and fun fact. And how this works. It executes both functions concurrently. Same as previous, if the dispatcher supports parallelism, it will be executed in parallel. It executes the lambda only if both computations succeed. This makes sense because the lambda is executed with the result of both computations. So we need both of them to succeed for the lambda to be called. There are actually overrides with more than two functions, so it doesn't have to be two. It can be 3 or 4, I don't remember the max limit. And similarly, a failure in one action cancels the other action. So if I go back, if image URL fails, breed fun fact will be canceled because it doesn't make sense to execute it if we know that the whole thing is going to fail. This helps in conserving resources, which I guess it's useful on Android. Yeah. Let's talk about racing. It's another functionality offered by Arrow. And a motivation for racing might be that if we want to introduce some local caching, if we notice that the breed names rarely change, so maybe we want to cache them for a few hours locally on the device, so the whole thing, again, is faster. And we want to get the data from the cache. If the cache is empty, only then we call the remote. If the remote call works, we want to save the result in the cache so that we can reuse it the next time we call our function. And a simple solution to this would look like this. We have a function breed names that returns the list of breed names. We first try to get the cached breeds that returns a nullable list. And if this is null, we will call the remote breeds that calls the backend. And then we return the result. And this works assuming that cached breeds will be super fast and remote is typically slower. However, there is a slight problem here. It actually makes, in the worst case, the breed names function to perform slightly slower because we are always trying to get from cache first, and that takes a non-zero time. Ideally, that will be super fast, so it won't be noticeable, but the topic of today is make it as fast as possible. And let's see how we can do that. So we can use the race end function from Arrow, which basically takes 2 or 3 functions. There's overloads for 2 or 3 functions. And it will concurrently run both of them. So it will concurrently run cached breeds and remote breeds. As soon as one of them completes, it will cancel the other one. Meaning there's one winner and the rest of the computations are canceled. That means that if the cache is empty, both functions start at the same time. And here I have a note that if the cache is empty, this one should never complete. And remote breeds will complete in, I guess, around 100 milliseconds. Let's say that's the API response time. The first one will get canceled, and we get the result of the second one. If the cache is full, again, both computations start at the same time, and hopefully the cache is super fast and it wins. The remote call will be canceled, and we get the result from the cache. Here we have also merge because the result return type is either, and we have list of strings on the right, list of strings on the left, and we merge the results together because it's always a list of strings. That's from the Arrow core library. You can check about it in the documentation. Here we wanted to focus on race. ArrowFX offers a bunch of other functions that I'm not going to discuss in details. For example, we saw that parmap will fail in case any computation fails. Sometimes that's not desirable. Parmap or accumulate would, again, fail the computation if one of the requests fails. It will fail the resulting computation, but it will execute all requests and collect all errors. This might be useful for form validation or some similar use cases where we still want to, or if you're syncing data to backend, and you might want to get all errors and then retry only the things that failed later. Similarly to parmap on a list, we have parmap on a flow. And here the resulting flow that's transformed will conserve the ordering of the elements as the original flow. And there is flow.parmap unordered, which doesn't guarantee preserving the elements. It will emit the new flow as soon as the computations complete that are passed to the lambda. That was all about ArrowFX. Now we move into Arrow resilience. Specifically the schedule data type. It allows us to compose powerful yet simple policies, and we can use those policies to either retry or repeat computations. The reasons we would like to repeat computations are because they failed, and the reasons we want to, repeat in case of success, and we would like to retry if they failed. And the schedule data type is an abstraction that allows us to define how many times we repeat, how long we wait between repetitions. The library offers some built-in schedules. For example, schedule.recurse. It's a policy that runs up to n times. In this example, I have 10 as the parameter, so it will run up to 10 times without a break between repetitions. We have schedule.spaced with a duration as an argument. A policy that repeats, that runs forever, but it takes 60-second breaks. We have schedule.exponential. We can customize it with a base duration, and it will do an exponential backing off in the runs. We have schedule.fibonacci, same idea, but Fibonacci numbers. Schedule.linear, and much more. Now, we can use these as they are, but maybe they're not very useful as they are, or we can use some combinators to combine them and build some more complex schedules. Some of those combinators are AND, that takes two schedules and runs if both of them want to run. That means it will run only if both of them agree that they need to run. and it will take the longer duration between their breaks, individual breaks. We have a do while that takes one schedule, and based on the duration, it can execute a predicate and decide if we want to continue running or stop. We have and then, which enables us to sequence the schedules. You have one schedule, you run it until completion, then you take a second schedule and you run that one until completion. Jittered is a function that takes a schedule and runs and adds a random noise, so it can slightly increase or decrease the duration. This is useful if you don't want to overload your backend in case there is like a deployment error or something. You want to add some random delay so you don't DDoS your backend from all your clients. Let's see some examples of how this can be used. First, the end combinator. In this example, we take a spaced schedule with 60 seconds break and a schedule that repeats 10 times, and we combine them with end. The resulting schedule will run with 60 seconds delay for up to 10 times. So it's taking the delay of the longer, which is 60 seconds. Between 60 seconds and 0, the bigger one is 60. And it taking the lower number of repetitions, which here is 10. So this is much more useful for practical applications. Do while. If we have an exponential schedule that will repeat exponentially forever, maybe we want to limit that to some reasonable amount of time a user will wait, something like 60 seconds. So here we use the do while operator, and we provide a function that returns true only if the resulting duration is less than 60 seconds. So we start with the 10 milliseconds exponential backing off, and as soon as the next break would come up to 60 seconds, it will give up. Another one is and then. So this basically allows us to chain schedules together. When the first one completes, it will run the second one. And here we're putting together the two complex schedules from the previous slides into one. We have an exponential backing off with 10 milliseconds delay. We cap that to a maximum of 60 seconds using do while. We use and then to change that with a spaced schedule with a 60 seconds delay that repeats up to 10 times. And in the end, we add a random noise so we don't overload the backend. And we can use this schedule both for retrying actions or repeating actions. For example, if we have our spaced schedule that repeats up to 10 times, we can use schedule.retry, and it will retry the breathe images function as long as it's failing or the schedule reaches its end. Similarly, we can repeat actions. I'm not sure why we would want to call this function 10 times in a row or something, but it is possible. This is more useful for, let's say, you want to periodically send a location update to your server or something like that. This is a really interesting data type that's inspired from Scala. The Arrow version is a port from Scala. And there is a full talk by the original author on YouTube available that you can watch if you want to hear more about the inspiration. Now that we learned a bit about Arrow FX and Arrow resilience and the scheduled data type, we can put all the stuff together. We can go back to our original function and implement it with parallelism, error handling, and retries. And that will look very similar. We have the same signature that returns a list of a pair of a breed name and an image URL. We call the breed names function. We use parmap not null to concurrently call the image URL function. We can also adjust the concurrency here if we wanted to. And then inside of the Lambda, we can use schedule.retry with any of the schedules we saw before and call the image URL function. If the schedule runs, or if the schedule finishes and the function still fails, we can return null. And because we have parmap not null, we filter out the null results. In conclusion, we can work with lists and concurrent operation using parmap. We can adjust things like concurrency and dispatches that we want the functions to run. We can use parmap not null if we have nullable computations. When we have independent computations, we can use parzip. It has multiple overloads with any number, with the different numbers of computations that we can run in parallel. For racing, we can use the raceend function. This is one use case is caching, but there are probably other use cases. And for resilience, we can use the schedule data type that has some built-in simpler policies and a bunch of combinators that allows us to combine them in complex and more powerful policies. That's all for today. Thank you for your attention.